Okay, let's get started. Everybody feeling good today? Not since you got in here? You were having a great day and then you got here?
Ron's not anymore. I told him.
What's wrong? Uh-oh. Okay. All right, so last class we were talking about improper integrals. Specifically, we were talking about type 1, where we have our integral, our limits of integration here, where one of them was going to infinity or possibly negative infinity. So we were looking at the area under a curve out in one direction forever or in the other direction forever. And I didn't write this formally on the board last time. I just did an example, and I told you that when we do these, we're going to have to do a limit. So what we do is we change the infinity to a t, and then we let that t go to infinity after we actually find the antiderivative. And then if we do this type of integral, where we go from negative infinity to some number, that we replace that negative infinity with t, find the antiderivative, and then take the limit at the end. I don't believe I had a chance to do one of these where we did the entire, did I do one? I don't think I did. You go from, if you want to do the area under a curve from negative infinity to infinity, that's the entire real number line. Then what we do is we break it up into two integrals. One of them going from negative infinity to c, and then from c to positive infinity. And c is just any number on the number line. It can be any number you want. All right, now the most common number used is 0. You go from like negative infinity to 0, and then you go from 0 to infinity. Now, all of these problems involve a limit, don't they? Like this is a problem, and then at the end we take a limit. This is a problem, at the end we take a limit. This integral actually becomes how many limits?
2 limits.
2 limits. And so all of these improper integrals, this type 1, since they involve limits, we need to remember that in Cal 1, when you take a limit of something, you don't always get an answer. When you take a limit, sometimes you get that the limit does not exist. Do you remember ever getting that? So in this case, we just need to be prepared for that sort of situation, where we just say the limit doesn't exist. Or sometimes the limit will actually be infinity or negative infinity. In either of those cases where we get the limit, can you open the door, please? Ruben? If the limit does not exist, the limit is infinite, or the limit is negative infinity, then what we say is that these integrals diverge. If you do the problems and the limits give you a nice finite number, like 2 or 10 or negative 5, whatever it is, then we say that the integral converges. And we write down what the answer is, 2, 10, whatever. All right, so the notes talk a little bit about this. Just remember that sometimes my answer to the problem is going to be diverges, and that's my conclusion. All right, so let's pick up with some examples here. Number 3, I really like number 3. This will be the first time we've seen one like this. So we have the integral from negative infinity to infinity of 1 over 1 plus x squared dx. So we look at this, and we notice the limits of integration are infinite. And so we know that we are integrating over the entire number line, right? We're looking at the function, whatever it's doing, and we're looking in both directions forever. That's my number line. I'm just kind of pointing out that we're looking in both directions forever. So to do this, I have to find some point anywhere on the number line where I'm going to split it and do like a left integral and a right integral. And I said the most natural choice is 0, right? That's the most natural choice. Now I also want to make sure that my function is defined on the entire number line, that there's nowhere where I have a discontinuity, where the denominator is 0. So is it possible to ever make that denominator 0?
No.
No, not if you're only using real numbers, right? You can't do it. So I should be free to go ahead and integrate without any issues. I will split this up into two integrals, integral from negative infinity to 0 of 1 over 1 plus x squared dx. And then I'll add that answer, because that's an area, right? That's an area underneath this curve. I will add that area to the area I get under the curve from 0 on to infinity. Each one of these problems is its own limit problem. So let's rewrite this integral as a limit. Let's rewrite this integral as a limit. So this equals limit. I'm going to let t go, let's see, let's start going around the room here. We're going to go off of Zach and Ivana's table. T is going to go to, on the first one, t is going to, careful. 0 is okay. See, I think. Look back at the definition I had up here. Where's it? Right here. Where do I have the limit written? There it is. If you go from negative infinity to a number, t is going to be replacing the infinite part. All right, so we're going to replace the infinite part with t. So t, I'm going to let go to negative infinity of the integral from where to where? T to 0. Of 1 over 1 plus x squared dx. Plus the next integral, which is another limit. This time I'm going to let t go to where? On this one. Positive infinity. And I rewrite the integral, and I go from 0 to t. Everyone understand? It's the infinite part that's being replaced with t, and then at the end I let that t go to infinity. See, we don't have a problem at 0. There's nothing even going on at 0. We plug 0 in this function, we just get 1. It's not really a point of interest to us. It's just a place to break it up into two integrals. That's all it is. All right, so now I'm at the point where it's time to find an antiderivative. And the good news is that the antiderivative of this is the same as the antiderivative of this, so you really only have to find one antiderivative. That's all, right? And what is the antiderivative of 1 over 1 plus x squared? Arctangent. So this now becomes the limit as t goes to negative infinity of arctangent of what? Arctangent of x. Okay, that's the antiderivative. But remember, I'm supposed to now put here a line behind it, and then put what two numbers there? 0 and t. So 0 on top, though, right? 0 here and t down here, like that. So I've done this part, this integral, and now I do plus, and then this integral. So plus limit t goes to positive infinity of the arctangent of x evaluated 0 and t up here. And that's the setup. Any questions? We're using the fundamental theorem of calculus, right? Just to go from there to here. Now, what I'll do is I'll plug in here. So remember, this line meant plug in 0 first, then subtract what you get when you plug in t, right? This one meant plug in t and then subtract what you get when you plug in 0. And the limits will be sitting outside in front of all those. So this becomes the limit as t goes to negative infinity of, I'm going to put in brackets, something minus something, close brackets, plus I'm going to have another limit as t goes to positive infinity of something minus something. You'll see all I'm doing is kind of setting up the fundamental theorem of calculus here, the evaluation theorem where I just plug in the numbers and I'm always going to get this format. We good? Plug in 0 into arctan, and what do you get? It's arctangent of 0. Uh-oh. 1. We all agree? Disagree? No calculators allowed. Arctangent of 0. All right, so let's see here. If I say tangent of an angle, let's say pi over 4, right? Ooh. Tangent of pi over 4. The answer is 1. Why is that 1? Because on the unit circle, if you go to pi over 4, you're right here, aren't you? And the point there is root 2 over 2, root 2 over 2, yeah? And so tangent of an angle is the y-coordinate divided by the x-coordinate. If I take this y-coordinate and divide it by the x-coordinate, I get 1, right? So that's what tangent of pi over 4 is. If I say over here, what's arctangent of 1, then the answer should be what? Pi over 4, the angle, right? And we're saying, okay, arctangent of 1 means at what angle do you get a ratio of 1? And so we would have to know pi over 4 is where you get the ratio to be 1, yes? But that's not what we're asking here. We're asking here is at what angle is the ratio 0? Here, y over x, 0 over 1 is 0, right? So at angle 0, you would get a 0 to come out of tangent, right? Now I heard someone say pi. Could it also be pi? 0 over negative 1, though, is what? Still 0, but it's not pi. Why? There's domain restrictions on arctangent function, just like there are domain restrictions on arcsine and arccosine. So when we look at arctangent, we are only allowed to look between negative pi over 2 and pi over 2. So this is pre-cal stuff, and I know maybe it's been a while, but we talked about it before, didn't we, at the beginning of class? No? When we were doing derivatives of inverse trig functions? A little bit, okay. Here's another approach, okay? That's one approach. Here's a different one. If you know what tangent looks like, and you need to know what tangent looks like, this is tangent x. Then when we're saying, when we're asking what is arctangent of 0, you're saying where is the y-coordinate 0 on this function? At 0, right? At 0, the y-coordinate is 0. But what's harder to look at, what's harder is when you have this, arctangent of 1, it's very difficult for people to be able to tell me, oh yeah, 1's here, and that they know it's pi over 4. That comes a little easier off the unit circle. Understand? Okay. So arctangent of 0 is 0. And then this one is arctangent of t, right? And then over here, I have what? Arctangent t. And then what do I get here? 0 again. Damn it, I just erased what I wanted. Oh well. I don't feel like rewriting everything, like getting rid of these zeros, so I'm just going to work with this. I'm ready to actually let t go to where these limits are saying they need to go to. All right? What happens if I let t go to negative infinity? I get arctangent of negative infinity. Negative infinity. Now we know that infinity is not a number, right? But what's happening is we're plugging in a number that's getting closer and closer to, well, negative infinity. It's getting very large and very negative, right? So we're saying to ourselves, at what angle on the tangent function are you getting a very, 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 very large negative number? So I had erased that picture. Where was it? negative pi over 2, right, is where we have the first vertical asymptote here. And you can see that the y-coordinate is a very, very large negative number the closer I get to negative pi over 2. So the limit is negative pi over 2. As I go further and further down, my x-coordinate, or the angle, is getting closer and closer to negative pi over 2. So this is negative pi over 2. I'll put it up here. Are there any questions with that? No? So we have here, hold on, negative, this is negative pi over 2. I've done the limit, that's why I didn't write it. Plus, now I'm saying let t go to positive infinity. Where is it? It's approaching pi over 2. And what happens if we add those two together? What do you get? 2 pi over 2, which is pi. Does this integral converge or diverge? Converge. If we have a finite number. Oh, yeah, I think, well, I'm not sure which, maybe continuity or something. So let me kind of recap what this problem is saying. If you were to graph 1 over 1 plus x squared, right? If you were to graph it, it would look like this. This is the graph of 1 over 1 plus x squared. What's the value of this function at 0? 1. And if you plug in 1, what do you get? 1/2. And if you plug in 2, what do you get? It's going to get smaller, right? Hold on a second. 1/5? Smaller? Yes? And then the other side, it would be the exact same thing, right? In fact, it would be a mirror image because this is an even function. But also, you could just check test numbers. So if you were to graph this, it would look like this. It would asymptotically approach 0 on each end. Get closer and closer to 0. What we just did says what? Who wants to tell me what we just did and what it means? Geometrically. The area underneath this thing is pi. If you take the area forever in both directions, if you were able to, you would get pi. Now we could never do that, but the further out you go, the closer and closer you get to pi. Make sense? And this ties into what I was talking about last time, probability density functions. And I said that if you have a probability density function in statistics, you want the area under the curve to be 1, right? So how could I tweak this function so that the area under here is 1? What would I have to do with it? Instead of using that function, what could I use? How about 1 over pi times that, right? Because if you integrate this from negative infinity to infinity, that looks like an 8. Infinity was trying to stand up there. Okay, so you go and pull out a 1 over pi. We know that this integral here turns out to be pi, right? And you scale it by 1 over pi. Now your answer is 1. That's why a lot of times in these statistics classes, there's statistics, you know how there's like physics classes for like physics 1 and 2 if you've never taken calculus, and then there's physics 1 and 2 if you have taken calculus, right? There's statistics courses where it's for people who have not taken calculus, and then others for people who have. So the statistics that involve calculus-based, they would look at things like this, all right? And you'll see a lot of times in those probability density functions, constants that are on the outside. You're like, where in the world, where's that 1 over pi coming from or whatever? It's because of the need to make it 1, so they scale it. All right. Next one. Integral. Negative infinity to infinity of x e to the x dx. Everybody take, let's say, 5 minutes and get the antiderivative of that. Just work on your own. See if you can get the antiderivative. We'll do all the limit stuff and fill that out, but we all know we need the antiderivative of that, don't we? So see if you can do that on the side. How many of you have this already? Yeah? Okay. How many of you know what you're supposed to do with it? And have it, or have it? Just trying to see. Okay. Maybe another minute. Okay, that's good enough. So who wants to volunteer what the antiderivative of x e to the x is? Go ahead.
I got x times e to the x minus e to the x plus c.
Plus c, but we won't need it, right? Okay, let's take a vote. How many of you are in favor of this? Okay, very good. So integration by parts, right? So once we have that, we can come back over here. This is going from negative infinity to infinity. I'm not concerned about any issues with this thing being undefined, because I don't have any division by anything, right? So I'm never going to have to worry about division by 0. E to the x is always defined, isn't it? The e to the x function looks like this, and we have no domain issues with that. So we should be free to go with this. So I'm going to break it into 2 problems, and each one of them is going to have their own limit. The first one, the limit's going to go from t goes to negative infinity, and I'm going to integrate from t to what? You want to pick 0 again? 0? We'll go to 0 of x e to the x dx. Then my next limit will represent the other integral, which will go from 0 to t. I'll go to positive infinity this time, of x e to the x dx. And then each of those, I can actually use the antiderivative now, right? And then set up my little bar on the right side for the evaluation theorem. So this becomes limit t goes to negative infinity of x e to the x minus e to the x evaluated here, plus limit t goes to infinity of x e to the x minus e to the x evaluated 0 to t. Questions? Yes. Yes, I can factor an e to the x out. So you could have e to the x times x minus 1. That would be an equivalent expression. All right, now I'm going to set up my little parentheses things that I've been doing. Limit t goes to negative infinity of, in brackets, parenthesis minus parenthesis, close it out. And then I have another one of those. Limit t goes to positive infinity, bracket, parenthesis, minus parenthesis, bracket. And let's try and plug 0 in first. If I plug 0 in, I get 0 minus what? 1, right? E to the 0 is 1. So I get negative 1. Now I plug t in. So I get t, e to the t, minus e to the t. Over here, I plug in t. I get t e to the t minus e to the t. And then when I plug in 0, again, I get negative 1, right? Limit time, right? We need to figure out what happens if I let t go to negative infinity right here. 0? Why would it be 0? What is this going to go to? Negative infinity? T is going to go to negative infinity. What's e to the negative infinity? That's the same as 1 over e to the infinity. What is 1 over e to the infinity headed towards? 0. Then minus what's e to the negative infinity? It's 1 over e to the positive infinity type, right? And that goes to 0. I'm going to talk about this more because I know that there's going to be people in there going, what in the hell is he talking about? All right, so do we agree that this is somewhat confusing a little bit? All right. How about over here? Let's talk about this one. We'll get back to that. T goes to positive infinity. That means this goes to what? Infinity. What's e to a huge positive number going to do? It gets big, right? This is infinity. But then we have what? Minus infinity. So this is like infinity minus infinity. What's infinity minus infinity? I don't know, right? This is what we call an indeterminate form in Calculus 1. We actually have to investigate that further. We can't say it's 0. Over here, we just said that this was headed to negative infinity, right? And we said that this part was headed to 0. Now again, I have to clarify why it is it's headed to 0. You're plugging in a huge negative number into this, right? So e to a huge negative number is the same as 1 over e to a huge positive number. And if you take a number and you fix a number like 1 and you put a very large number on the bottom, that ratio goes down to 0, doesn't it? Yes? So this guy right here is headed to 0. And then minus, what is this one headed to? Same thing, e to the negative infinity, that goes to 0. What is this? An indeterminate form. We actually don't know. Again, that's a Calculus 1 problem. That's something we scratched our heads about in calculus, and we had a way of getting around it. Subtracting 0 from it doesn't really matter, so that doesn't really factor into much. So there are two things I have to figure out right now. I have to figure out what's happening here and what's happening here. So I'm going to go and just kind of scratch all this for now, go to the side and do some scratch work, and I'm going to evaluate those two limits. And let's see if you can remember how we do those. Show of hands, L'Hopital's rule. Now remember that's it, show of hands, L'Hopital's rule? L'Hospital's rule? Okay. It's spelled like hospital, but it's L'Hopital. All right, so I am interested first in this limit. I want to know what the limit is as t goes to negative infinity of t e to the t minus e to the t. Now, Ruben pointed out that we could factor out, that's a negative infinity, sorry, an e to the t and get t minus 1, right? We could do that? We already know, because of what I just explained, that we're getting some sort of infinity times 0 here, right? That's what we're getting? And that's an indeterminate form. How is it that you handle indeterminate forms that have this pattern to them? Does anyone remember? Do what? That's how we use L'Hopital's rule, right? L'Hopital, you do a derivative. But to use L'Hopital, you have to have this happening. Okay, so L'Hopital only works if you have the form of infinity over infinity or 0 over 0. And it can be plus or minus here, it doesn't matter. But your expression must be a ratio. The top must be going to infinity and the bottom must be going to infinity, or the top must be going to 0 and the bottom must be going to 0. We don't have that here. We have a product. So does that help? Anyone remember how to do it? No?
I never did it.
No? You didn't do L'Hopital's rule?
That's the way
Okay. So we should talk about L'Hopital's rule. I recommend that if you haven't seen L'Hopital's rule, come by my office. I'm here, like 3 or 4 hours, at least 2 hours before class. Most of the time I'm here at 9 a.m., but the last week or two has been crazy. So L'Hopital's rule is one of those things that you just need to know how to use. It's a very nice rule, right? Everyone who's used it? Very nice? Yes? Okay. So look, the approach to this is that in L'Hopital's rule you need a ratio, right? We have a product. We're going to turn the product into a ratio. So what we'll do is we'll grab one of these and we'll drop it to the bottom and we'll look at it as a fraction. So look, I'm going to take one of these factors, and I'm going to pick the one that looks easier to work with once it's dropped down, which is the e. So if I drop that e down, doesn't it become e to the negative t? I mean, that's just another way of writing that, right? But now it looks like a fraction. So let's look real quick. What happens if t goes to negative infinity? Negative infinity minus 1, negative infinity. So the top's going to negative infinity. Now be extremely careful here because we've changed something. T goes to negative infinity. Negative infinity would really be what? Positive infinity, right? E to the positive infinity would become huge, right? Become infinite. So the bottom is actually going to positive infinity now. Now this looks like what we need for L'Hopital's rule. Got it? So L'Hopital's rule says that as long as that form is in place, your next equal sign, you apply the rule. And some books use an H like that. Some people like myself use an L. They let people know they're applying the rule. Yeah, have y'all seen that? Or just an H without a circle around it or something? No? Someone seen something else? You have to write it down, okay? Because, well, not have to, but it's good math penmanship, because it's like me saying, if I write down like x squared plus 1 over 3x cubed plus 1, and I say that equals 2x over 9x squared, what did I do to get from here to here? I did the derivative on top and bottom. That's L'Hopital's rule, isn't it? That's what L'Hopital's rule is. You take derivative top and bottom separately. But algebraically, these are not the same thing, right? So you can't say this is equal to this, ever. So you have to indicate you did something that makes them equal. And the L'Hopital's rule is what allows it to be equal. So, okay, we're going to symbolize that we are using L'Hopital's rule. We rewrite the limit. Limit t goes to negative infinity. And then L'Hopital's rule, Luke, all you do is take derivative of the top and bottom. But it has to look like this. Okay, you have to have infinity over infinity or 0 over 0. So the derivative of the top is what? 1 over the derivative of the bottom. Be careful. E to the negative t times negative 1. So negative e to the negative t, isn't it? Because chain rule, you have to take derivative of the top, or the exponent. Now, let t go to a negative infinity again. And what we're checking for is to see if L'Hopital's rule actually allowed us to get to an answer. So if we let t go to negative infinity, the bottom here, e to the negative infinity, that thing blows up, it gets huge, infinitely huge. 1 divided by a huge number, doesn't matter, it's negative, right? 1 over a big negative number is still going to approach what? 0. This goes to 0. And that's the beauty of L'Hopital's rule, is that whatever the original limit does, or sorry, I should say it this way, whatever this limit does, the original limit does the same thing. So our conclusion is that that was 0. We good? So back in our work, we're going to know that that first one went to 0. Now, what was the other limit I said we had to look at? Limit t went to infinity. What was it? T e to the t minus e to the t. That was the other one? And we said this one had the form of what? When we did this, it looked like infinity minus infinity. Can we use L'Hopital's rule for this? No, because it's subtraction. The one we just did before this was a product. And we had to change the product into a ratio, didn't we? When you have this, the normal protocol is to try and factor. Try and turn subtraction into multiplication. And then maybe you go from the multiplication into the ratio if you need to. But we already saw, Ruben pointed out that we could factor this, right? So it would be e to the t times t minus 1. And what happens if I let t go to infinity here? So this becomes what? Infinite, right? So now this has the form of infinity times infinity minus 1? Infinite. What's infinity times infinity? Infinity. So this is infinite. Subtraction, we don't know. Multiplication, guaranteed. If it's infinity times 0, we don't know. If it's infinity times infinity, we do know, right? Big, huge positive number times big, huge positive number is a big, huge positive number. So, what does this mean? Go back to our limits. When we did our limits, let's see, I've forgotten. Go back to that line we had. Didn't we have a -1? Like in that first bracket, we had a -1? And then minus what we just got in that limit that we had to go investigate, which was 0, right? And then plus, I'm not writing the limits anymore because I took the limits, right? Plus, and then I had 2 sets of parentheses here. This last one was -1, right? And we just determined that this is what? Infinite. And as soon as you see infinity, you're done. This thing diverges. It diverges because you have a term in here. One of your integrals, right, becomes infinitely large. The area becomes infinite. Are we good? Do you understand? Any questions? This is the graph of x e to the x. And I want you to see something. This first set of brackets here was actually the area from -infinity to 0, wasn't it? What would that area have been? -1. Do you see that left side of the graph? We actually have our graph going below, and then it tapers out like that. That area to the left of 0 is -1. But when you bring in the other side, it's pretty obvious that if we go out that direction forever, that area just gets infinitely large. Do you see it? All right, so there's a lot going on in there, right? Little L'Hopital in there, little integration by parts. So how about a formula? Just something to add to your list of things to remember. Anytime you do an integral from 1 to infinity of 1 over x to a power, so we're using p as power. If p is greater than 1, right? It says if p is greater than 1, it converges. If p is less than or equal to 1, it diverges. So you tell me here real quick. Does that integral converge or diverge? It converges, right? Because p is 7. So if I were to graph this function, the area from 1 to the right forever is a finite number, isn't it? If I change this to 1 over the 7th root of x, it will what? Diverge. Because p would be 1/7 in this case, which would be less than 1, right? Well, let me throw one little twist in this. How about this? What would the integral from 1,000 to infinity of 1 over x do? What would this do? Converge or diverge? You thinking converge? The p is larger than 1, right? P is 2, which is bigger than 1, and according to that it converges. But that's if the integral starts where? 0. At 1, right? But do you think I can still say it converges?
Yes.
What happens if I plug 1 into this? I get 1, right? What happens if I plug in 2? Gets smaller, right? This thing is diving down towards the x-axis, isn't it? And I know that if I start at 1 and I go out forever, the number is fixed. The number is finite, right? And I want you to not start at 1. I want you to start way out here at 1,000 and only look from 1,000 to the right. That's still got to be convergent then. Because if the whole thing is convergent, then if you take out a part of it, it's that what's left is still going to be a finite number. Right? It has to be. So that would also be convergent. Now, what's the answer? You actually have to go work it out, right? But if you know it converges just by looking at it because of that. All right, that wraps up the type 1 improper integrals. Now we're going to look at type 2. Type 2 improper integrals are where you have infinite integrands. So I'll give you an example of one, all right? I'm going to give you an example before I actually talk about how we're going to address it. How about integral from 2 to 10 of 1 over x minus 5 dx? Or you know what, let's do x minus 2. Start out this way. So how about before we do this, I ask you what the antiderivative is. You're happy to see that, right? You're really happy to see this. 1 over x minus 2 dx, the antiderivative is natural log of x, absolute value of x minus 2 plus c, and that's all good, right? So that part of it's not an issue. So you might be thinking right now, okay, well, all I have to do, right, is, don't write this down, is just do that, and then plug in 2 and plug in 10, and then be done. But there's a problem. Something we missed when we were looking at this. The bottom can be 0, can't it? Where? At 2. And guess what? That's where we're starting, at 2. So somehow we have this discontinuity as part of our interval of integration. So do you see how this is different than the last type that we were looking at? In the last type, we always had infinity out here, right? Either infinity here or negative infinity here or both. That's type 1. Type 2, there's not infinities here. There's actually something wrong with the integrand. That's why they're called infinite integrands. So what if we graph, let's just graph that function real quick. Let's just graph. What does the function f of x equals 1 over x minus 2 look like? Well, you know, if this goes back to college algebra, this is a rational function. The denominator is 0 at 2, and so we have a vertical asymptote there. And then if you draw it, you'd get something that looks like this. All right? That's what it would look like. If you wanted to, you could get on your calculator or computer and you could graph it just to confirm that this is what's happening. So if I am supposed to take the area between 2 and 10, then I know this end is no problem, right? Like I don't have anything. I'm stopping. I'm not going to infinity, right? So I'm stopping. I'm trying to find this area, but do you see what's happening here? Right? It's actually becoming infinite, isn't it? And so we have an infinite integrand. Our integrand is infinite, as opposed to our limit is not infinite. It's the integrand that becomes infinite. Do you see the difference? Okay. I'm just trying to get you to understand the names of these things and why they call them what they call them. So could it be possible that that area is actually finite? Well, we saw the other way that it could be, right? And sometimes it wasn't. So how do we deal with this? Well, here's what we do. Guess what it's going to involve?
L'Hopital?
Maybe a L'Hopital, but it's going to be a limit, just like the other one. What we're going to do is say, hey, look, I know I can't be 2, right? If I try and plug 2 in, I'm done. So why don't I get close to 2 and not actually ever get there, but get as close as I actually ever want to, like do the limit. So this will work as follows. I'm going to start the problem by drawing the interval out of where I'm integrating on. So, I'm going to do 2, I'm going to do 10 here, and then I'm going to take a look at the integrand. I'm going to make sure there's no problems here, but there is. The problem is at 2. So I'm going to come over here and I'm going to circle 2, and I'm going to put like a dotted line to let myself know that my function is like undefined here. And that means if I'm trying to find the area in this region, right, then when I approach 2, when I use a limit, I'm going to have to approach 2 from which side, the left or the right? The right, because the region we're interested in, the area, is the stuff to the right of 2, isn't it? It's this stuff over here, that area. So when I write my limit, I can't just write limit x approaches 2. I have to actually approach 2 from a certain side. So this will be, I don't know, see if you can guess what this will be. Limit, what do you think? We'll use, well, be careful, we can't use x because x is the variable in here. We'll use t because t is our limit, our limits of integration. So t is going to approach what? 2. How do I say from the right? Little plus sign up here. Of integral, right? Where to where? T to 10. And then 1 over x minus 2 dx. I mean, tell me if you understand. Like, do you agree with what's happening here? We are saying, look, I'm going to find the area between t and 10. And then I'm going to let that t get closer to 2 from the right side. And that will give me the area that I'm looking for, without actually ever having to be t is 2. All right. So this becomes the limit as t approaches 2 from the right. And we already found that antiderivative, didn't we? It was natural log of the absolute value of x minus 2. And then I have my evaluation bar that I put out here, t and 10. Then I'm going to write limit. I'm going to do a bracket, 2 sets of parentheses, evaluation theorem, plug in. So let's plug 10 in first. 10 goes in there. We get natural log of what? 8. I don't need the absolute value anymore because 8's a positive number, so I'm not concerned about that. Natural log of 8. And then over here, natural log of absolute value of t minus 2, right? Questions? What's next? Pardon? Minus? Yeah, let's do the limit now, right? We've done all the calculus part, the antiderivative part, right? We've got all that set up. Now we need to just figure out what happens when t actually approaches 2. So let's let t approach 2. If I replace this with 2 here, this is getting really close to the natural log of what? 0. And the natural log of 0 is undefined, isn't it? But we know what happens to natural log when we approach 0, don't we? So you have to go back and you have to understand what the graph of natural log looks like. This is the graph of the natural log. I think I drew this last class, didn't I? Maybe not. think I remember drawing it. I did draw it. And I kind of went off topic for a second, and then I came back, and I drew this. And I said, what happens is we go this way, and I said it grows, right? And then I went this way, and then I said, what happens when it approaches 0? And everyone said it goes to where? Negative infinity. And that's exactly what we're doing here, right? We're letting t approach 2, which makes this quantity in here approach 0, and the natural log of something that approaches 0 is going to approach negative infinity. See, we're not actually there. We're not actually at 0. We're a little bit bigger than 0, right? Because that number is going to be a little bit bigger than 0. So the answer here is what? This right here gives me negative infinity. And what can you tell me then? Positive infinity. But as soon as I see infinity, diverges. Diverges. We're going to do another one of these. But before I do, I want to address something we talked briefly about last class, and I didn't get to really conclude what happened. So this is going to be I'm going to go back to a type 1 real quick, and I'm going to make quick work of this. What's the area under the cosine curve from 0 to infinity? Remember I asked you about this, and like some people were saying 0, and some people were saying other things, and then we talked about, well, if you stop it at some multiple of something, you would get an answer. Okay, but let's follow the actual format. First thing I'm going to do is make sure there's no problems with the function, like it's never undefined. Cosine's always defined, right? So I can just go straight to the integral. This is going to be the limit as t goes to infinity of the antiderivative. What's the antiderivative? Sine x. And I'm going to be evaluating from 0 to t, right? Then you plug in t, you get sine t, minus you plug in 0, sine of 0 is 0. Oh, I forgot my limit. Limit t goes to infinity. Minus 0. And what is the limit as t goes to infinity of sine of t? So that means if you look at the sine function, as you go out to the right, is it headed anywhere? Is it headed to one value? No. It oscillates, right? This oscillates back and forth. So there's no way anyone's ever going to tell me that this limit exists. This limit does not exist. And what happens as soon as I see does not exist, infinity or negative infinity? I say it diverges. So this diverges. The reason I was thinking about that is because with these integrals, when you see infinity, I know that you might want to just write your answer, infinity. What we're looking for is divergence. So you write down diverges. I don't think I would take off too much if you put infinity and boxed it. I mean, I would take something off, but you need to conclude from that that the integral diverges. Does divergence mean it goes to infinity? That the area is infinite? Is that what divergence means? No. It just means that it doesn't converge. I mean, it's, right? If you say that, I'm trying to think of a good analogy without getting in trouble. Divergence, no, I better just stay away from that. Never mind. I'll just stay away from that. I heard about a professor at Texas, where were they? I just heard about this today. They're in the news. My colleague was telling me about someone who was making some political statements in his class, and he's been teaching for 20 years, and some liberal group got a hold of it, or a conservative group got a hold of it. One of the students recorded it, and then it just, now he has to, like, I don't know, he might lose his job. It's just whatever. Can't say anything these days, but. All right, another example of this. I wasn't going to be political, but I didn't want people to take it the wrong way.
And you're recording yourself.
And I'm recording myself. I'm kind of like setting myself up for failure here. That's one of my big fears, that one day this whole idea of trying to make this a better thing for students is going to backfire on me. All right, this one. Yeah, let's look at this one. What about integral 0 to 2 of 1 over the square root of 2 minus x dx? This is really, really a similar problem to what we just did. It is not a type 1, right? It's pretty easy to see it's not type 1. The only way you're going to see it's type 2 is if you investigate the interval first and make sure that when you're looking at your interval that there aren't any discontinuities in that interval. And there are, aren't there? 0, the denominator will be 0 if x is 2, which is one of the endpoints of our interval. So 2 is a bad place. And so I'm going to need to approach it from the left side. Agreed? All right, take about 2 minutes, maybe 3 minutes, to go ahead and get me the antiderivative of this real quick. Go ahead. See if you can get that antiderivative in 2.5 minutes, starting 5 seconds ago. Uh-oh. Sign-in sheet's coming around. Anybody have it yet? Okay. So, who's volunteering this one? Go ahead. All right, what do you got?
Negative 2 over 2 minus x.
Over 2 minus x?
Square root.
2 over it?
Oh, no. Never mind. I didn't even write that down. Yeah, just
I agree that there's a root.
negative 2 times square root.
There you go. Okay. All right. Let's see how many agree. It's like half. Anyone have something else for me to put up here? Go ahead, Ron. That- No? Then you're okay with this? So you have the same thing? Okay. So no one is disagreeing then? It's correct then? If we don't disagree, it's correct? It's right. Bring out the 1/2. This is a 1/2. Bring out the 1/2. Half of that is -1. Subtract 1 from these, you get -1/2. That's what drops it down. And then derivative of what's inside is -1, and that kills off the -1 that's out there. This is correct. Basic U substitution. All right. Both integrals I've asked you all to do today are what I would consider to be probably not even ever going to be something you would see on a test. Those are way too easy. I mean, those are too basic. So if you're struggling with those, that's, alarm bells should be going off in your head, because that would be not expected on a test. All right, with that nice, thought, let's just move on. Limit. I just want to be honest with you. I don't want you to think that I'm giving you those as like examples of test problems. That should be pretty easy. It should only take you a few minutes at the most. All right, so I'm going to set up a limit. I'm going to let what approach what, and from what side? T approach 2 from the left of the, we already did the antiderivative. So this thing, -2 root 2 minus x, evaluation bar 0 to t, right? Replacing the 2 with t. Now you could get an integral like that in a problem like this, yes, but just not by itself. Like, integrate that. I feel bad that I told you like that was too easy, but. So I'm going to set up my brackets now, my 2 sets of parentheses. Plug t in, I get -2 times root 2 minus t, and then I plug in 0. What happens when I plug in 0? -2 times root 2? Okay. And now we let t go to 0. Not t go to 0, t go to 2. So I'm approaching 2, right? Right in here. 2 minus 2 is 0. Now, why is it important that I was approaching from the left side? Let me try and explain that, why it's so important here. Here's 2. I'm approaching from this side, right? So the numbers that I'm actually plugging in for t are smaller than 2, aren't they? Numbers like 1.9999, very, very, very close to 2 without actually being greater than 2. And so if I take 2 and I subtract 1.99999, I'm going to get a very, very tiny positive number. And that's good, because I need to take square root of it. So it's defined. If I were to be approaching 2 from the other side, then those numbers would be bigger than 2, right? 2 minus something bigger than 2 would be a very, very small what? Negative number, and you can't take square root of a negative number. So just purely by domain issues, we have to approach 2 from the left side. So if you were to say, oh, I forgot that I had to come in from one side, it's not that big of a deal, then you can't tell me that that's going to be equal to 0. Because from one side it is, from the other side it's not even defined. All right. But it is approaching 0, isn't it?
Yep.
Which means this whole thing's gone. Which means my answer is what?
-2 root 2.
But then negative, so 2 root 2? So this integral converges. Now you don't have to write converges. If you're giving me a numerical answer, you're kind of implying that, hey, that does go to a number. But if it diverges, you need to write down diverges. Questions? Oh, I like this one. I like it a lot. I like it a lot. What? No. No. Well, sometimes I see the problems up there and I'm like, hey man, I like that problem. Who came up with that? Oh, I came up with that problem. No, most of these problems are usually examples out of the book, just to keep it kind of in line with the author. So let me pick your brain here. Like, what are you thinking here? You see this? What's your thought process? I want to know, like, what are you thinking first, then next? Like, anyone? Anything. Factor. I'm hearing factoring. People are saying factor. Is everyone thinking factor? All right. Well, I don't mind factoring it. Not sure why you want me to, but I'll do it. Do you want me to factor an x out like that? Okay. Now what are you thinking? Partial fraction. So you're already starting to think about antiderivatives, and you're thinking that's going to be a partial fraction problem. You all see that? Okay. I don't mind us going and doing that. We can do the partial fractions. Are there any issues that we have with this integral? Is this just a normal integral, or is this an improper integral? Yeah, we got to see where it could be 0 and see if we're integrating on that. So we are integrating from 1 to 4, aren't we? And do we have an issue somewhere in there? Only at 4, right? There's an issue at 0. Is 0 in here? 0 is not in here. I'm looking between here and here, right? I'm focusing all my attention in there. So I have an issue at 4, but not at 0. So I do have an issue here, which means I'm going to need to approach 4 from the left-hand side, right? So this will turn into a limit, but I will also need to get the antiderivative. So I think this is where you would go do that now, right? Anybody have that yet? That is not an example of a rational partial fraction problem on a test either. This one is too easy also. It's just a factorable quadratic. It breaks up into 2 natural logs. And I have to do a little more work than that on the test. So shall we break this up? I'm gonna work fast.
Problems in like such questions where you're testing this on the rest of the stuff, not just integrating.
I'm sorry?
You can give this kind of a problem in such a question. Where
Oh yeah,
you
in
actually-
this context, this would be appropriate. But as an integral by itself, this would, if I'm going to be testing you on partial fractions, I'm guessing you're probably going to have to do some long division. You're probably going to have to show me several of the techniques that are required for it. You know.
And here you're actually looking for us to solve the rest of the thing.
Yeah, I'm more focused on a problem like this. Are you picking up on this thing? And are you going to address it with a limit or not? Because if you don't bring the limit in, then there's a big problem with it. All right, so I'm going to do this quick. I'm going to rewrite this as a over x. We have 2 distinct linear factors, right? And that gives me 1 equals a times x minus 4 plus bx. And then when I start plugging in to kill things off, I get a is negative 1/4, and I get b is 1/4. Anyone agree? Yeah. Okay. So that's what you should get if you do your partial fractions correctly. Now back to this. This integral becomes a limit as what approaches what, and from which side? T approaches 4 from the left of the antiderivative, right? What's the antiderivative? 1/4 natural log of x. Good. Negative 1/4, right? Negative 1/4 natural log of x, absolute value. And then from the b, we have a 1/4 over that one, so 1/4 natural log of x minus 4. And then we want to evaluate that, right? From where? 1 to t. Is everyone okay on where that all came from? Like I'm skipping quite a bit of work here just to save time. You feel like you could get that on your own?
So like right after we do partial fraction, so right after we finish doing the antiderivative, then you want us to set the limit.
Yes. Yeah. Well, as soon as you write the next line, you should have a limit. If you're going to not write, if you're going to rewrite it, as soon as you need to, I don't know, you could do it later as long as you do it at some point,
But just like as soon as you can would be like the fastest, like the most clear you can.
Yeah. All right, let's plug in the two things. Limit t goes to infinity, or no, infinity. T goes to 4 from the left. And then I have my two sets of parentheses. This might get kind of tight here. Let's see. Plug in t first. Negative 1/4 natural log t. Definitely going to be tight here. I'm going to have to erase some stuff. Plus 1/4 natural log of t minus 4. That's what I get when I plug in t. What happens when I plug in 1? So minus, I'm going to have to carry this one down here. I'm out of room. So plug in 1. It's natural log of 1. 0. So that's all gone. 1 here. 1 minus 4 is negative 3. Absolute value. Natural log of negative 3. But there's a 1/4 in front of it. So shouldn't this just become 1/4 natural log of 3?
Well, you don't need the absolute value.
I don't need the absolute value. But it's not wrong to put it either. The absolute value of 3 is 3. All right. Now t is going to go where? To 4, right? From the left. What's natural log of 4? I don't know, something, right? Natural log of 4, whatever that is. But when I try and plug 4 in here, what do I get? You get natural log of 0. And what did we say happens to the natural log function as you approach 0? It becomes infinite, negative infinity, right? And so I can say what then? This diverges. All right, this next example is the last one I'll do today. Integral 3 to 5 x over cube root of x minus 4 dx. Okay, I'd like everyone to work on the antiderivative of that right now. Take a few minutes to find the antiderivative of this, because you're going to need it. And then we'll talk about whether or not we have a problem, if it's an improper integral, and how we're going to deal with it. But you're going to have to be able to integrate before you can do any of that. So, and then I'll ask for a volunteer to share with me what the antiderivative is and how they got it. you get it, Ron? What'd you use?
I'll try it last week.
Hmm?
UV substitution.
You didn't use this?
Yeah. And because I separated out first, when I did the substitution, and then that's how I got home. And then I got into B, B and DU is over here, and I just simplified it out.
So you did integration by parts?
Yeah.
Is that what you did? Okay. Okay, I think that's probably enough time. If you're hung up on it, that's okay. But how many of you are trying just a basic substitution? Anyone just using a basic substitution? Anyone trying integration by parts? Anyone trying trig substitution? What else? What are y'all trying? There's only like 4 people responded. So what are y'all trying? Integration by parts? All right, so I'm not sure which technique is going to work here. I'm just going to show you what I would do. I'm not sure if this is going to work, but I have a good feeling about it. I'm going to let u be equal to the cube root of x minus 4. I know that doesn't seem like a very natural thing to want to do, because the du is ugly, isn't it? And right, the derivative of that's ugly, and I doubt it appears here. But I showed you this once. If I cube both sides, I get that, don't I? Yes? And now if I take the derivative on both sides, the derivative of the left side is 3u squared du. And the right side, the derivative is what? Dx. So I will be able to replace this with what? With u. And I will be able to replace dx with 3u squared du, right? The only thing really left for me to determine is what the x will become, which I can use this to say that u cubed plus 4 is x. Now, I believe integration by parts will also work for this, but it's a little uglier. So what would my new integral look like? I'd have x right here, which is u cubed plus 4 over what? Oh, this is just u times dx, which is 3u squared du. One of the u's cancels with one factor there. And then all I have is u cubed plus 4 times 3u du. And I can distribute the 3u through. And I get what? Integral. You want me to pull the 3 all the way out? Okay, I'll pull the 3 all the way out. U to what power? 4th plus 4 times u du. So that's just passing that u through. And now that's just power rule. So the antiderivative of this will be 3/5 u to the 5th plus what? It's the antiderivative of 4u. 2u squared, but then times 3, so 6u squared plus a constant. But what's u? This cube root thing, right? So this would be 3/5 cube root of x minus 4 to the 5th power plus 6 times the cube root of x minus 4 to the 2nd power. I'm not saying that's the only way to do it, just that is a particular way to do it. That would be a candidate for an integral on a test. Something that's not as natural, not as fluid as the two prior to this, right? Where you have to kind of struggle with it a little bit, try something. All righty. So now let's go back and look at that integral that we had. And let's address some issues that we had with it. 3 to 5, x over cube root x minus 4 dx. Do I have a problem at 5? If I plug 5 in here, is it okay? Yes? If I plug 3 in here, is it okay?
No, because, yeah.
It's a cube root. It's a cube root. You can take a cube root of a negative number. That's all right. So see, you don't have any problems at the endpoints, right? But you do have a problem where?
At 4.
At 4. And 4 is in there, isn't it? This is a very dangerous integral because what happens is that people will overlook the fact that there's a discontinuity at 4. They'll get the antiderivative, they'll plug in the two endpoints, and they'll say they're done. What they lose with that is the fact that there's a discontinuity in there. So the graph is there. See it below the function? That's the graph. And you see we have the function becoming infinite there at 4? Yes? So I need to be very careful when I'm doing this problem to draw out my number line where I'm integrating, 3 to 5, circling where I have a discontinuity, and realizing that I'm going to have to approach 4 from what? Both sides. Guess what that means you're going to have to do? 2 integrals. You have to split it up into 2 integrals. So this integral actually becomes the integral first from 3 to 4 of the function, and then plus the integral from 4 to 5 of the function. For
Both have different limits on it.
That's right. So on this one, you have to set up the limit, right? As t goes to what? 4 from which side?
Negative.
Left side, the negative. So this integral right here represents this region right here. Call that integral A. This is integral A. Integral B here is going to be this one right here. So integral A is limit as t approaches 4 from the left. This one is limit as t approaches 4 from the right. And then you have to go through the whole business of plugging things in and setting it up and figuring it out, right? We already have the antiderivative, though. So this is your take-home quiz to be turned in at the beginning of next class. Finish it off. I already got you the antiderivative, right? So you just finish it off. Turn it in next class. We good? All right. What are we doing next time we meet? Talking about the exam, right? We've pretty much covered the 2 types. I mean, I could do more and more examples. Well, there's only one more in my notes. So I'll offer that one as a bonus. How about that? You like bonuses?
5.
5? Yeah. Do it separately than this, though. So if you're going to do the bonus, do that on a separate piece of paper. I'm not saying it's bonus because it's harder. I'm just saying because I didn't do it in class, you go do it and show me you did it, and I'll give you a bonus. So next time we will talk about the exam, right? Maybe, I mean, time is not something we have a lot of in this class. We're supposed to talk about on the 13th. We're supposed to be doing improper integrals next class, but I'm saying we're done with improper integrals. So I would really like to try and spend Tuesday, maybe I can come up with a set of problems and just come into class and be like, here, why don't you all look at those and see what you think of that. And make sure I tell you that's not a review for the test, but it's just a practice, right? Hmm? It's a non-review review. Yes. Can you use, what is that? The trig sub. Why don't we do what we did last time? Didn't I offer bonus if you don't use anything? No, I didn't in the class. Let's do it that way. You're allowed to have those formula sheets on your test, the ones that are on the website, the whatever, 6, 8 pages, whatever it is. Everybody gets that, right? If you take the test without any other additional resources, like the, what is that, partial fractions? Is that the partial fractions one? Or trig sub? Okay. If you do it without any of the trig sub formulas, then I'll give you an additional 2 or 3 points. Okay? Just a little 2 point for, but if you feel like you need it, you can use it. We'll talk more about that next class. Everyone have a good rest of your day and a good weekend, if I don't see you. Remember that all of the solutions to the homework problems are online. So you should be able to do all the odds for this section. Bye. See you later. Well, it's 5 through 31 odds. 6 for page 360. It's 5 through 31 odds. That's the homework that would come out of the improper integral section.
Am I wrong? You can look on my test.
And you're still doing that bonus for those other problems too?
I am, yes.
The one recording on my
Yep. Yes?
Do we have to, what's it called? Do we have to use what's the fundamental theorem of calculus for those problems, 1 through 40, or are we just taking the
Yeah, I don't really care. I mean, it's really more of an exercise that'll hopefully benefit you. I mean, I think we're all aware that the antiderivative part is the main part of it. But if you want to practice just to get used to plugging numbers in and seeing how some things, sometimes you have to like combine natural logs together to get the match the back of the book sort of thing. It's good exercise.
Yeah, because there was one that I did, I think yesterday. It was like one you showed us last class, where it was an odd function.
Okay.
Like tangent, but I at least saw it